A wallpaper group is a mathematical classification of a two-dimensional repetitive pattern, based on the symmetries in the pattern. Such patterns occur frequently in architecture and decorative art. There are 17 possible distinct groups. Wallpaper groups are two-dimensional symmetry groups, intermediate in complexity between the simpler frieze groups and the three-dimensional crystallographic groups. Introduction. Wallpaper groups categorize patterns by their symmetries. Subtle differences may place similar patterns in different groups, while patterns that are very different in style, color, scale or orientation may belong to the same group. Consider the following examples. Examples A and B have the same wallpaper group. It is called P4M in the IUC notation and 442 in the Orbifold notation. Example C has a different wallpaper group, called P4MG or 4 times 2. The fact that A and B have the same wallpaper group means that they have the same symmetries, regardless of details of the designs, whereas C has a different set of symmetries despite any superficial similarities. A complete list of all 17 possible wallpaper groups can be found below. Symmetries of patterns equals, a symmetry of a pattern is, loosely speaking, a way of transforming the pattern so that it looks exactly the same after the transformation. For example, translational symmetry is present when the pattern can be translated some finite distance and appear unchanged. Think of shifting a set of vertical stripes horizontally by one stripe. The pattern is unchanged. Strictly speaking, a true symmetry only exists in patterns that repeat exactly and continue indefinitely. A set of only, say, 5 stripes does not have translational symmetry. When shifted, the stripe on one end disappears, and a new stripe is added at the other end. In practice, however, classification is applied to finite patterns, and small imperfections may be ignored. Sometimes two categorizations are meaningful, one based on shapes alone and one also including colors. When colors are ignored there may be more symmetry. In black and white there are also 17 wallpaper groups. For example, a colored tiling is equivalent with one in black and white with the colors coded radially and a circularly symmetric barcode in the center of mass of each tile. The types of transformations that are relevant here are called Euclidean plane isometries. For example, if we shift example B 1 unit to the right, so that each square covers the square that was originally adjacent to it, then the resulting pattern is exactly the same as the pattern we started with. This type of symmetry is called a translation. Examples A and C are similar, except that the smallest possible shifts are in diagonal directions. If we turn example B clockwise by 90 degrees, around the center of one of the squares, again we obtain exactly the same pattern. This is called a rotation. Examples A and C also have 90-degree rotations, although it requires a little more ingenuity to find the correct center of rotation for C. We can also flip example B across a horizontal axis that runs across the middle of the image. This is called a reflection. Example B also has reflections across a vertical axis, and across two diagonal axes. The same can be said for A. However, example C is different. It only has reflections in horizontal and vertical directions, not across diagonal axes. If we flip across a diagonal line, we do not get the same pattern back. What we do get is the original pattern shifted across by a certain distance. This is part of the reason that the wallpaper group of A and B is different from the wallpaper group of C. History, a proof that there were only 17 possible patterns was first carried out by Evgraf Fedorov in 1891 and then derived independently by George Pascal Cublier in 1924. The proof that the list of wallpaper groups was complete only came after the much harder case of space groups had been done. Formal definition and discussion. Mathematically, a wallpaper group or plane crystallographic group is a type of topologically discrete group of isometries of the Euclidean plane that contains two linearly independent translations. Two such isometry groups are of the same type if they are the same up to an affine transformation of the plane. Thus, for example, a translation of the plane does not affect the wallpaper group. The same applies for a change of angle between translation vectors, provided that it does not add or remove any symmetry. Unlike in the three-dimensional case, we can equivalently restrict the affine transformations to those that preserve orientation. It follows from the Bieber-Bach theorem that all wallpaper groups are different even as abstract groups. 2D patterns with double translational symmetry can be categorized according to their symmetry group type. Isometries of the Euclidean plane isometries of the Euclidean plane fall into four categories. Translations, denoted by TV, where V is a vector in R2. This is the effect of shifting the plane applying displacement vector V. Rotations, denoted by RC, I, where C is a point in the plane, and I is the angle of rotation. Reflections, or mirror isometries, denoted by FL, where L is a line in R2. This has the effect of reflecting the plane in the line L, called the reflection axis or the associated mirror. Glide reflections, denoted by GL, D, where L is a line in R2 and D is a distance. This is a combination of a reflection in the line L and a translation along L by a distance D. The independent translations condition the condition on linearly independent translations means that there exist linearly independent vectors V and W such that the group contains both TV and TW. The purpose of this condition is to distinguish wallpaper groups from frieze groups, which possess a translation but not two linearly independent ones, and from two-dimensional discrete point groups, which have no translations at all. In other words, wallpaper groups represent patterns that repeat themselves in two distinct directions, in contrast to frieze groups, which only repeat along a single axis. It is possible to generalize this situation. We could for example study discrete groups of isometries of Rn with M linearly independent translations, where M is any integer in the range 0 per mole currency Ma per mole currency N. The discreteness condition the discreteness condition means that there is some positive real number I micron, such that for every translation TV in the group, the vector V has length at least I micron. The purpose of this condition is to ensure that the group has a compact fundamental domain, or in other words, a cell of non-zero, finite area, which is repeated through the plane. Without this condition, we might have for example a group containing the translation Tx for every rational number x, which would not correspond to any reasonable wallpaper pattern. One important and non-trivial consequence of the discreteness condition in combination with the independent translations condition is that the group can only contain rotations of order 2, 3, 4, or 6. That is, every rotation in the group must be a rotation by 180 a degree, 120 a degree, 90 a degree, or 60 a degree. This fact is known as the crystallographic restriction theorem, and can be generalized to higher dimensional cases. Notations for wallpaper groups Crystallographic notation. Crystallography has 230 space groups to distinguish, far more than the 17 wallpaper groups, but many of the symmetries in the groups are the same. Thus we can use a similar notation for both kinds of groups, that of Carl Hermann and Charles Victor Mauguin. An example of a full wallpaper name in Hermann-Mauguin style is P31M, with 4 letters or digits. More usual is a shortened name like C2M or PG. For wallpaper groups the full notation begins with either P or C, for a primitive cell or a face-centered cell. These are explained below. This is followed by a digit, N, indicating the highest order of rotational symmetry, 1-fold, 2-fold, 3-fold, 4-fold, or 6-fold. The next two symbols indicate symmetries relative to one translation axis of the pattern, referred to as the main one. If there is a mirror perpendicular to a translation axis we choose that axis as the main one. The symbols are either M, G, or 1, for mirror, glide reflection, or none. The axis of the mirror or glide reflection is perpendicular to the main axis for the first letter, and either parallel or tilted 180 a degree/n for the second letter. Many groups include other symmetries implied by the given ones. The short notation drops digits or an M that can be deduced, so long as that leaves no confusion with another group. A primitive cell is a minimal region repeated by lattice translations. All but 2 wallpaper symmetry groups are described with respect to primitive cell axes, a coordinate basis using the translation vectors of the lattice. In the remaining two cases, symmetry description is with respect to centered cells that are larger than the primitive cell, and hence have internal repetition. The directions of their sides is different from those of the translation vectors spanning a primitive cell. Hermann-Mauguin notation for crystal space groups uses additional cell types. Examples: P2, primitive cell, two-fold rotation symmetry, no mirrors or glide reflections. P4mg, primitive cell, four-fold rotation, glide reflection perpendicular to main axis, mirror axis at 45 degrees Celsius 2 mm, centered cell, two-fold rotation, mirror axis both perpendicular and parallel to main axis. P31m, primitive cell, three-fold rotation, mirror axis at 60 degree. Here are all the names that differ in short and full notation. The remaining names are P1, P3, P3m1, P31m, P4, and P6. Orbifold notation, Orbifold notation for wallpaper groups, advocated by John Horton Conway, is based not on crystallography, but on topology. We fold the infinite periodic tiling of the plane into its essence, an orbifold, then describe that with a few symbols. A digit, n, indicates a center of n-fold rotation corresponding to a cone point on the orbifold. By the crystallographic restriction theorem, n must be 2, 3, 4, or 6. An asterisk indicates a mirror symmetry corresponding to a boundary of the orbifold. It interacts with the digits as follows: digits before denote centers of pure rotation. Digits after denote centers of rotation with mirrors through them, corresponding to corners on the boundary of the orbifold. A cross, A, occurs when a glide reflection is present and indicates a cross gap on the orbifold. Pure mirrors combine with lattice translation to produce glides, but those are already accounted for, so we do not notate them. The no symmetry symbol, O, stands alone, and indicates we have only lattice translations with no other symmetry. The orbifold with the symbol is a torus. In general, the symbol O denotes a handle on the orbifold. Consider the group denoted in crystallographic notation by C2m. In Conway's notation, this will be 2 times 22. The 2 before the says we have a two-fold rotation center with no mirror through it. The itself says we have a mirror. The first 2 after the says we have a two-fold rotation center on a mirror. The final 2 says we have an independent second two-fold rotation center on a mirror, one that is not a duplicate of the first one under symmetries. The group denoted by P2GG will be 22A. We have 2 pure two-fold rotation centers, and a glide reflection axis. Contrast this with P2MG, Conway 22, where crystallographic notation mentions a glide, but one that is implicit in the other symmetries of the orbifold. Coxeter's bracket notation is also included, based on reflectional Coxeter groups, and modified with plus superscripts accounting for rotations, improper rotations and translations. Equals why there are exactly 17 groups equals, an orbifold can be viewed as a polygon with face, edges, and vertices, which can be unfolded to form a possibly infinite set of polygons which tile either the sphere, the plane or the hyperbolic plane. When it tiles the plane it will give a wallpaper group, and when it tiles the sphere or hyperbolic plane it gives either a spherical symmetry group or hyperbolic symmetry group. The type of space the polygons tile can be found by calculating the Euler characteristic, I equals VE plus F, where V is the number of corners, E is the number of edges and F is the number of faces. If the Euler characteristic is positive, then the orbifold has an elliptic structure. If it is 0, then it has a parabolic structure, that is a wallpaper group. And if it is negative, it will have a hyperbolic structure. When the full set of possible orbifolds is enumerated, it is found that only 17 have Euler characteristic 0. When an orbifold replicates by symmetry to fill the plane, its features create a structure of vertices, edges, and polygon faces, which must be consistent with the Euler characteristic. Reversing the process, we can assign numbers to the features of the orbifold, but fractions, rather than whole numbers. Because the orbifold itself is a quotient of the full surface by the symmetry group, The Orbifold Euler characteristic is a quotient of the surface Euler characteristic by the order of the symmetry group. The Orbifold Euler characteristic is 2 minus the sum of the feature values, assigned as follows: a digit n before accounts as n, a digit n after accounts as /2n, both and a count as 1. The no symmetry a degree counts as 2. For a wallpaper group, the sum for the characteristic must be 0. Thus the feature sum must be 2. Examples: 632, 5/6 plus 2/3 plus 1/2 equals 2, 3 times 3, 2/3 plus 1 plus 1/3 equals 2, 4 times 2, 3/4 plus 1 plus 1/4 equals 2, 22 1/2 plus 1/2 plus 1 equals 2. Now enumeration of all wallpaper groups becomes a matter of arithmetic, of listing all feature strings with values summing to 2. Feature strings with other sums are not nonsense. They imply non-planar tilings, not discussed here. Guide to recognizing wallpaper groups. To work out which wallpaper group corresponds to a given design, one may use the following table. See also this overview with diagrams. The 17 groups. Each of the groups in this section has 2 cell structure diagrams, which are to be interpreted as follows. On the right-hand side diagrams, different equivalence classes of symmetry elements are colored differently. The brown or yellow area indicates a fundamental domain, that is the smallest part of the pattern that is repeated. The diagrams on the right show the cell of the lattice corresponding to the smallest translations. Those on the left sometimes show a larger area. Group P1 equals. Orbifold notation, a degree, Coxeter notation, a plus, 2, a plus or, a, plus a, plus, lattice, oblique, point group, C1, the group P1 contains only translations. There are no rotations, reflections, or glide reflections. Examples of group P1. The 2 translations can each have different lengths, and can form any angle. Group P2 equals. Orbifold notation, 2222, Coxeter notation, a, 2, a, plus, lattice, oblique, point group, C2, the group P2 contains 4 rotation centers of order 2, but no reflections or glide reflections. Examples of group P2. Group PM equals. Orbifold notation, Coxeter notation, a, 2, a plus or, a plus, 2, a, lattice, rectangular, point group, D1, the group PM has no rotations. It has reflection axes, they are all parallel. Examples of group PM, the first 3 have a vertical symmetry axis, and the last 2 each have a different diagonal one. Group PG equals. Orbifold notation, a, Coxeter notation, a, 2, plus, a plus or, a plus, 2, a, plus, lattice, rectangular, point group, D1, the group PG contains glide reflections only, and their axes are all parallel. There are no rotations or reflections. Examples of group PG. Without the details inside the zigzag bands, the mat is P2MG. With the details but without the distinction between brown and black, it is P2GG. Ignoring the wavy borders of the tiles, the pavement is P2GG. Group CM equals. Orbifold notation, a, Coxeter notation, a plus, 2 plus, a, or, a, 2 plus, a plus, lattice, rhombic, point group, D1, the group CM contains no rotations. It has reflection axes, all parallel. There is at least one glide reflection whose axis is not a reflection axis. It is halfway between 2 adjacent parallel reflection axes. This group applies for symmetrically staggered rows of identical objects, which have a symmetry axis perpendicular to the rows. Examples of group CM. Group P2M equals. Orbifold notation, 2222, Coxeter notation, a, 2, a, or, a, Coxeter notation, 4, 1 plus, 4, or, 1 plus, 4, 1 plus, lattice, rectangular, point group, D2, the group P2M has reflections in 2 perpendicular directions, and 4 rotation centers of order 2 located at the intersections of the reflection axes. Examples of group P2M equals group P2MG equals Orbifold notation, 22, Coxeter notation, a, 2, plus, a, or, a, 2, a, plus, lattice, rectangular, point group, D2, the group P2MG has 2 rotation centers of order 2, and reflections in only one direction. It has glide reflections whose axes are perpendicular to the reflection axis. The centers of rotation all lie on glide reflection axes. Examples of group P2MG equals group P2GG equals Orbifold notation, 22 a, Coxeter notation, a, 2, plus, a, 2, plus, Coxeter notation, 4 plus, lattice, rectangular, point group, D2, the group P2GG contains 2 rotation centers of order 2, and glide reflections in 2 perpendicular directions. The centers of rotation are not located on the glide reflection axis. There are no reflections. Examples of group P2GG equals group C2M equals Orbifold notation, 2 times 22, Coxeter notation, a, 2 plus, a, Coxeter notation, 4, 2 plus, lattice, rhombic, point group, D2, the group C2M has reflections in 2 perpendicular directions, and a rotation of order 2 whose center is not on a reflection axis. It also has 2 rotations whose centers are on a reflection axis. This group is frequently seen in everyday life, since the most common arrangement of bricks in a brick building utilizes this group. The rotational symmetry of order 2 with centers of rotation at the centers of the sides of the rhombus is a consequence of the other properties. The pattern corresponds to each of the following, symmetrically staggered rows of identical doubly symmetric objects, a checkerboard pattern of 2 alternating rectangular tiles, of which each, by itself, is doubly symmetric, a checkerboard pattern of alternatingly a 2-fold rotationally symmetric rectangular tile and its mirror image. Examples of group C2M equals group P4 equals Orbifold notation, 442, Coxeter notation, 4, plus, lattice, square point group, C4. The group P4 has 2 rotation centers of order 4, and 1 rotation center of order 2. It has no reflections or glide reflections. Examples of group P4, a P4 pattern can be looked upon as a repetition in rows and columns of equal square tiles with 4-fold rotational symmetry. Also it can be looked upon as a checkerboard pattern of 2 such tiles, a factor smaller and rotated 45 a degree. Equals group P4M equals Orbifold notation, 442, Coxeter notation, 4, lattice, square point group, D4, the group P4M has 2 rotation centers of order 4, and reflections in 4 distinct directions. It has additional glide reflections whose axes are not reflection axes. Rotations of order 2 are centered at the intersection of the glide reflection axes. All rotation centers lie on reflection axes. This corresponds to a straightforward grid of rows and columns of equal squares with the 4 reflection axes. Also it corresponds to a checkerboard pattern of 2 of such squares. Examples of group P4M, examples displayed with the smallest translations horizontal and vertical. Examples displayed with the smallest translations diagonal. Equals group P4MG equals Orbifold notation, 4 times 2, Coxeter notation, 4 plus, 4, lattice, square point group, D4, the group P4MG has 2 centers of rotation of order 4, which are each other's mirror image, but it has reflections in only 2 directions, which are perpendicular. There are rotations of order 2 whose centers are located at the intersections of reflection axes. It has glide reflections axes parallel to the reflection axes, in between them, and also at an angle of 45 a degree with these. A P4MG pattern can be looked upon as a checkerboard pattern of copies of a square tile with 4-fold rotational symmetry, and its mirror image. Alternatively it can be looked upon as a checkerboard pattern of copies of a horizontally and vertically symmetric tile and its 90 a degree rotated version. Note that neither applies for a plain checkerboard pattern of black and white tiles. This is Group P form. Examples of Group P for MG equals Group P3 equals. Orbifold notation, 333, Coxeter notation, 3, 3, 3, plus or, 3, 3 plus, lattice, hexagonal, point group, C3. The group P3 has three different rotation centers of order 3, but no reflections or glide reflections. Imagine a tessellation of the plane with equilateral triangles of equal size, with the sides corresponding to the smallest translations. Then half of the triangles are in one orientation, and the other half upside down. This wallpaper group corresponds to the case that all triangles of the same orientation are equal, while both types have rotational symmetry of order 3, but the two are not equal, not each other's mirror image, and not both symmetric. For a given image, three of these tessellations are possible, each with rotation centers as vertices, that is, for any tessellation two shifts are possible. In terms of the image, the vertices can be the red, the blue or the green triangles. Equivalently, imagine a tessellation of the plane with regular hexagons, with sides equal to the smallest translation distance divided by h3. Then this wallpaper group corresponds to the case that all hexagons are equal and have rotational symmetry of order 3, while they have no mirror image symmetry. For a given image, three of these tessellations are possible, each with 1/3 of the rotation centers as centers of the hexagons. In terms of the image, the centers of the hexagons can be the red, the blue or the green triangles. Examples of Group P3 equals Group P3M1 equals. Orbifold notation, 333, Coxeter notation, 3, 3, 3, or, 3, 3, lattice, hexagonal, point group, D3. The group P3M1 has three different rotation centers of order 3. It has reflections in the three sides of an equilateral triangle. The center of every rotation lies on a reflection axis. There are additional glide reflections in three distinct directions, whose axes are located halfway between adjacent parallel reflection axes. Like for P3, imagine a tessellation of the plane with equilateral triangles of equal size, with the sides corresponding to the smallest translations. Then half of the triangles are in one orientation, and the other half upside down. This wallpaper group corresponds to the case that all triangles of the same orientation are equal, while both types have rotational symmetry of order 3, and both are symmetric, but the two are not equal, and not each other's mirror image. For a given image, three of these tessellations are possible, each with rotation centers as vertices. In terms of the image, the vertices can be the red, the dark blue or the green triangles. Examples of Group P3M1 equals Group P31M equals. Orbifold notation, 3 times 3, Coxeter notation, 6, 3 plus, lattice, hexagonal, point group, D3. The group P31M has three different rotation centers of order 3, of which two are each other's mirror image. It has reflections in three distinct directions. It is at least one rotation whose center does not lie on a reflection axis. There are additional glide reflections in three distinct directions, whose axes are located halfway between adjacent parallel reflection axes. Like for P3 and P3M1, imagine a tessellation of the plane with equilateral triangles of equal size, with the sides corresponding to the smallest translations. Then half of the triangles are in one orientation, and the other half upside down. This wallpaper group corresponds to the case that all triangles of the same orientation are equal, while both types have rotational symmetry of order 3 and are each other's mirror image, but not symmetric themselves, and not equal. For a given image, only one such tessellation is possible. In terms of the image, the vertices cannot be dark blue triangles. Examples of Group P31M equals Group P6 equals. Orbifold notation, 632, Coxeter notation, 6, 3, plus, lattice, hexagonal, point group, C6. The group P6 has one rotation center of order 6, which only differ by a rotation of 60 a degree. It has also two rotation centers of order 3, which only differ by a rotation of 120 a degree, and 3 of order 2. It has no reflections or glide reflections. A pattern with this symmetry can be looked upon as a tessellation of the plane with equal triangular tiles with C3 symmetry, or equivalently, a tessellation of the plane with equal hexagonal tiles with C6 symmetry. Examples of group P6 equals group P6 equals. Orbifold notation, 632, Coxeter notation, 6, 3, lattice, hexagonal, point group, D6, the group P6 has one rotation center of order 6. It has also two rotation centers of order 3, which only differ by a rotation of 60 a degree, and 3 of order 2, which only differ by a rotation of 60 a degree. It has also reflections in 6 distinct directions. There are additional glide reflections in 6 distinct directions, whose axes are located halfway between adjacent parallel reflection axes. A pattern with this symmetry can be looked upon as a tessellation of the plane with equal triangular tiles with D3 symmetry, or equivalently, a tessellation of the plane with equal hexagonal tiles with D6 symmetry. Thus the simplest examples are a triangular lattice with or without connecting lines, and a hexagonal tiling with one color for outlining the hexagons and one for the background. Examples of group P6 lattice types. There are 5 lattice types or brevet lattices, corresponding to the 5 possible wallpaper groups of the lattice itself. The wallpaper group of a pattern with this lattice of translational symmetry cannot have more, but may have less symmetry than the lattice itself. In the 5 cases of rotational symmetry of order 3 or 6, the unit cell consists of 2 equilateral triangles. They form a rhombus with angles 60 a degree and 120 a degree. In the 3 cases of rotational symmetry of order 4, the cell is a square, and the 5 cases of reflection or glide reflection, but not both, the cell is a rectangle. Special cases, square. In the 2 cases of reflection combined with glide reflection, the cell is a rhombus. It may also be interpreted as a centered rectangular lattice. Special cases, square, hexagonal unit cell. In the case of only rotational symmetry of order 2, and the case of no other symmetry than translational, the cell is in general a parallelogram. Special cases, rectangle, square, rhombus, hexagonal unit cell. Symmetry groups. The actual symmetry group should be distinguished from the wallpaper group. Wallpaper groups are collections of symmetry groups. There are 17 of these collections, but for each collection there are infinitely many symmetry groups, in the sense of actual groups of isometries. These depend, apart from the wallpaper group, on a number of parameters for the translation vectors, the orientation and position of the reflection axes and rotation centers. The numbers of degrees of freedom are 6 for P2, 5 for P2m, P2mg, P2gg, and C2m, 4 for the rest. However, within each wallpaper group, all symmetry groups are algebraically isomorphic. Some symmetry group isomorphisms, P1, Z2, PM, ZA, DA P2m, DA, DA. Dependence of wallpaper groups on transformations. The wallpaper group of a pattern is invariant under isometries and uniform scaling. Translational symmetry is preserved under arbitrary bijective affine transformations. Rotational symmetry of order 2 ditto. This means also that 4 and 6-fold rotation centers at least keep 2-fold rotational symmetry. Reflection in a line and glide reflection are preserved on expansion-contraction along, or perpendicular to, the axis of reflection and glide reflection. It changes P6m, P4mg, and P3m1 into C2m, P3m1 into Cm, and P4m, depending on direction of expansion-contraction, into P2m or C2m. A pattern of symmetrically staggered rows of points is special in that it can convert by expansion-contraction from P6m to P4m. Note that when a transformation decreases symmetry, a transformation of the same kind obviously for some patterns increases the symmetry. Such a special property of a pattern is not counted as a form of extra symmetry. Change of colors does not affect the wallpaper group if any 2 points that have the same color before the change also have the same color after the change, and any 2 points that have different colors before the change also have different colors after the change. If the former applies, but not the latter, such as when converting a color image to one in black and white, then symmetries are preserved, but they may increase, so that the wallpaper group can change. Web demo and software. Several software graphic tools will let you create 2D patterns using wallpaper symmetry groups. Usually you can edit the original tile and its copies and the entire pattern are updated automatically. MAD Pattern, a free set of Adobe Illustrator templates that support the 17 wallpaper groups. TESS, a Mauguin tessellation program for multiple platforms, supports all wallpaper, frieze, and rosette groups, as well as Heish tilings. Kali, online graphical symmetry editor applet. Kali, free downloadable Kali for Windows and Mac Classic. Inkscape, a free vector graphics editor, supports all 17 groups plus arbitrary scales, shifts, rotates, and color changes per row or per column, optionally randomized to a given degree. Symmetry Works is a commercial plugin for Adobe Illustrator, supports all 17 groups. Arabesque is a free standalone tool, supports a subset of wallpaper groups. See also, List of planar symmetry groups, aperiodic tiling, crystallography, layer group, mathematics and art, M.C. Escher, point group, symmetry groups in one dimension, symmetry groups in one dimension, tessellation. Notes. References, The Grammar of Ornament, by Owen Jones. Many of the images in this article are from this book. It contains many more. J. H. Conway. The Orbifold Notation for Surface Groups. In M. W. Liebeck and J. S. A. X. L. Groups, Combinatorics and Geometry, Proceedings of the LMS Durham Symposium, July 5 Euro 15, Durham, UK, 1990. London Math. SOC. Lecture Notes Series 165. Cambridge University Press, Cambridge pages 438 to Euro 447, J. H. Conway. H. Bergill, C. Goodman Strauss, The Symmetries of Things. Worcester M.A., A. K. Peters. ISBN 1-56881-220-5. Gra 1/4 NBAUM, Branco. Shepard, G. C. Tilings and Patterns. New York, Freeman. ISBN 0-7167-1193-1. Pattern Design, Louis F. Day. External links, The 17 Plane Symmetry Groups by David E. Joyce, Introduction to Wallpaper Patterns by Chaim Goodman Strauss and Heidi Bergill, description by Silvio Levi, example tiling for each group, with dynamic demos of properties, overview with example tiling for each group, Escher Web Sketch, a Java applet with interactive tools for drawing in all 17 plane symmetry groups, Barak, a Java applet for drawing symmetry groups. A JavaScript app for drawing wallpaper patterns, Bearbeitungen zum geometrischen Motiv der Pelter, 17 kinds of wallpaper patterns. The 17 symmetries found in traditional Japanese patterns.